What are reciprocals? Reciprocals are when the numerator becomes a denominator and the denominator becomes a numerator. For instance, 1 over 2 will become 2 over 1. For functions, if the original function is fx equals to ax plus b, the reciprocal will be fx equals to 1 over ax plus b. Now we are going to talk about asymptotes. What are asymptotes? Asymptotes are restrictions of a reciprocal functions. They are vertical asymptotes and horizontal asymptotes. Vertical asymptotes are the restrictions of x, and horizontal asymptotes are the restrictions of y. How do we find the vertical asymptote and the horizontal asymptote of a reciprocal function? For a vertical asymptote, we can use x equals to negative b divided by a. From here, as you can see, the denominator can never be 0. That's why if x equals to negative b divided by a, the denominator will be 0. That is why this is the restriction of x, and this is the vertical asymptote of x. And since you know that the numerator is already 1, y can never be 0. That is why the horizontal asymptote is y equals to 0. Here we have an example. If the original function is x plus 1 equals to fx, then the reciprocal function will be 1 over x plus 1 equals to fx. How do we find the vertical asymptotes and the horizontal asymptotes? Just by looking at the graphs. Just how we do it. We know that the denominator can never be 0, so x plus 1 cannot be 0. So x cannot be negative 1. And therefore we know that the vertical asymptote is x equals to negative 1. Horizontal asymptote, we also know that 1 can never be 0, so y can never be 0. So this is the graph. This is the parent function which is fx equals to x plus 1, and these two are the reciprocals, which are fx equals to 1 over x plus 1. Now we see here, now we know that the vertical asymptote is x equals to negative 1. We can see that the reciprocal graph will never touch x minus 1, x equals to negative 1. So it's very close, but it never passes through. And for the horizontal asymptote, the reciprocals do not pass through it as well. From this graph, we can also know that the x-intercept of the parent function is the vertical asymptote of the reciprocal function. Now we head into quadratic functions. The reciprocals of quadratic functions are similar to the linear functions. However, there are a few different cases. Like a quadratic function may have two zeros. That makes it have two restrictions for its reciprocal. For example, 1 over x minus 2 times x plus 3 equals to fx. Its restrictions would be x cannot be negative 3 and x cannot be negative 2. This would make two vertical asymptotes. However, since the numerator is 1, the restrictions for y will be the same and y will never be 0. That makes it horizontal asymptote will be y equals to 0. This is the graph of the original function. X plus 3 times x minus 2 equals to fx. As you can see, this is how the graph looks like, and the minimum point is 0 and negative 6. For the reciprocal graph, this is how it looks like, and because you can know that there are two zeros, so there are two vertical asymptotes, which are x equals to negative 3 and x equals to 2, and the horizontal asymptote will be y equals to 0. And the local maximum point of this graph would be negative 0.5 and 0.16. Another case is when the quadratic function has zeros that are undefined. For example, this one, fx equals to x squared plus 25. The 0 of x will be root of negative 25. This is undefined. That's why the restrictions of the reciprocal function will be undefined as well. So there are no restrictions on x. It means there are no vertical asymptotes. But however, the same as all the other graphs that are shown, the restrictions of y are still 0. So the horizontal asymptote is still 0. This is the graph of the original function, which is concave up and have a minimum point of y equals to 25. and its reciprocal is concave down and has a maximum of 0.04. How do we know that it's 0.04? We take the minimum point of the parent function and put it into the reciprocal, we will get 0.04. This is how we look for the maximum point for the reciprocal. And there are no zeros, that's why there are no vertical asymptotes. That means x can be any number, but however y still cannot be 0. That's why the function will never touch the x-axis. The last case is when the quadratic function will have the two same zeros. For example, for this function, the zeros will both be -1. So for the reciprocal function, the restrictions will also both be -1. And the horizontal asymptote will still be the same, which is y equals to 0. Now we look at the graph. The graph has the vertical asymptote of x equals to -1, but the graph extends to both negative infinity x and positive infinity x, and the y-intercept of the graph is 1.
I'm gonna teach you about chapter 3.3, and we can start off by what are rational functions. Rational functions are actually polynomial functions over polynomial functions. They can exist in a form of ax plus b over cx plus d, which is actually this stands for the leading coefficient. This is the unknown, and this is also another coefficient of the first polynomial, and this is the second polynomial. Now, rational functions are actually a part of reciprocal functions. So guys, how do we determine a vertical asymptote of a rational function? We must make sure that the denominator must be a 0 to be undefined, as said in chapter 3.1 and chapter 3.2. Okay, so let's have an example. Let's say we have a function of 2x plus 1 over x plus 2. Now, the denominator of this function, which is x plus 2, must be a 0. So instead, we should write x plus 2 equals 0. So if we shift the 2 over, we shall have x, which is equivalent to -2, to sum in this equation, make it to 0. So guys, how do we actually find the horizontal asymptotes for the rational function 2x plus 1 over x plus 2? First, you have to multiply the two polynomial functions by 1 over x, which will make it reciprocal, such as this one here, which is actually reciprocal. Now, 1 over x is actually heading towards infinity, which is also equivalent to 0, as infinity is actually uncountable. And so when you divide 1 over x, which is infinity, which is also equivalent to 0, you get 0 here. These two of these will actually have 0, and that you will have left is only 2 over 1, and therefore the horizontal asymptote will be equivalent to 2, which is there.
So here we have come to this part. We have to solve for the reciprocal equations. So let's have a simple one first. 3 over x plus 3 equals to 2. So here is the algebraic way, and it's obviously very easy. So you just multiply x plus 3 over there, and you get the answer, obviously. But also remember that x cannot be -3. That's one of the answers also. Or you can use the graphical method, and you can find the intersection point. Simple. So here you have to solve another more complex equation, and as you can see, first you factorize it to make it more easy to see, and you can see that there's a similarity here. So what you do is just multiply all of the factors, and then you can simplify. So we simplify it to this, but remember about the asymptotes, and then we solve it for x equals to 3. This is the algebraic method. Another way is to use the graph, where we just have to find the crossing point of the graph. So as this is the graph of this minus this, so we can have the crossing of the x-intercept there. And as you see, it's 3 also, and here is 3. Alright, so now we're trying to solve inequalities as here like this. So we're trying to find y is more than or equals to 2. And there's one way we can do it, which is the graph. And let's draw the graph of y equals to half of 1 over x squared. And we draw another graph of y is equals to 2. And then you find the parts where the graph is more than y equals to 2. And then you have the answers from there. Another way is to use an algebraic method where we have to use intervals. So how to find these intervals is that we have to solve this also. So 1 over x squared equals to 2. And we say that x is not equals to 0 because x squared cannot be equal to 0. And then we solve it, getting this answer. And then we have these 4 intervals between -half, 0, and half. And then we substitute one value that is in between these inequalities into this equation. From there, we find whether y is more than 2 or less than 2. So from this figure, we can easily see that y is more than 2 when x is between negative square root of half and 0, and x is between 0 and square root of half. Alright, so here we have another inequality that we have to solve. And as you can see, it's a quadratic over a quadratic, which is a bit harder. And then the first thing we do is factorize. And then we get the roots. And we get the asymptotes. And then after that, we have to do it onto an interval table. And then you have to test each value to see whether it's less than or more than 0, because see what we want more than 0 here. And then we find it's very obvious that this is more than 0, this is more than 0, and this is more than 0. So those are your answers. Another way is to use the graph. And it's very easy to see that this is more than 0, here is more than 0, and there is more than 0.
Here is actually an equation, a rational function of x squared minus 3x minus 10 over x squared plus 8x plus 12. In order to solve this rational function, we have to simplify, we have to factorize the polynomial equations, which will end up to be x plus 2 multiplied by x minus 3 over x plus 2 and x plus 6. Now from chapter 3.2, the denominator, which is this part here, cannot be 0. So the asymptotes for the restrictions for the rational functions would be x minus 2 and also negative 6. But for this rational function, which has been factorized, it can be simplified. So they both, x plus 2 actually both exist in the numerator and the denominator, so they will be cut off among each other. So instead, we shall only see a visible restriction, which is x equals to negative 6, which shall be your vertical asymptote, which is here. Now, even though negative 2 is a restriction, but it's not seen in the overall equation, which will be fx equals to x minus 5 over x plus 6, which is not seen here. Negative, this root is not seen in this function, but it still exists as a restriction, as there's no lines which can actually does not pass this point here at x minus 2, and therefore it is actually called a hidden discontinuity. I'm not sure if that's very correct. Where it has a gap in the middle, which is actually represented by a hole here, and it will continue after this point here, which is all the way to infinity. And in order to find this point here, this hidden discontinuity, we have to put, we already know that x is negative 2 for this point here. And in order to find the y values, we have to sub in negative 2 into this equation, which will make negative 7 over 4, which will be our y. And there you have it.
Time moves fast while we're silently waiting, holding back heavy heart.